We're not going to review the math, just because math is what math is. I again forgot my microphone. Math is what math is. So what we're going to talk about are the kind of principles of physics that he includes in the chapter, and I'm going to tell you how they apply to what we do. So we'll start on page 23 with standard units of measurement. There is one thing that I've failed to mention on in the basic math, and that is graphing. So graphing, what we have, and you're not physically going to graph things, especially in this class, still burgers. But you are going to see graphing, especially next semester, and when we get into imaging, and when Amy does radiobiology. So you have two axes on a graph. You have vertical and horizontal, x-axis and y-axis, right? So what we're going to study and what we're going to look at in graphing eventually are a number of different things. So if we're talking about radiation dose, then we're going to look at graphing on that. So in diagnostic imaging and in ionizing radiation, we say that there is no minimum safe dose, right? So what that means is that there is no threshold to the dose, and then the dose is accumulative, so that the more dose you get, the more likely you are to have some sort of ill effects. So what we've got there then is a straight line. The greater the dose, the greater the effect, cause and effect, right? But Amy's going to get a little bit more specific next semester, and she's going to talk about determinative, stochastic, non-stochastic, and what you're going to find is that certain doses for certain effects may have a threshold dose. So what you may have is a situation where there's no dose, or let's say there's a little bit of dose, and with that dose there's a little bit of effect, likelihood of effect, but it's going to get to a point where a little bit of increase in dose may have a greater effect than at low doses. So we're going to look at graphing eventually. We're also going to look at graphing in imaging, and how it is that our computer algorithm controls our imaging characteristic, contrast, and density. So you make an image, and it applies the data that you get to a specific set of parameters that just looking at those parameters, it just doesn't make sense, a whole lot of sense. So, and it's again a graph of a different sort, where you've got exposures and you got all these lines that go, they're long lines and little lines and gaps in between and things like that. It's just visually, you don't make a whole lot of sense out of it. So what we use is what we used to use in screen film radiography is a S-shaped curve that we call the Herter and Dreifield, or H&D curve. And that's what we use as a representation of what that looks like. Okay, so and we'll get more specific in that, but in your computer algorithm that you use to process your images, they look like that, but we use that to make better sense of it. And we'll, again, dial that in a whole lot tighter next semester and explain what that means. So, graphing. So then, now we're going to talk about, the basic physics of imaging. And what we need to understand is that we have to have certain things that are measurable, consistently measurable. And what we're going to use is standards, international SI units for our measurements, and there's fundamentally three. The easiest one is seconds. So seconds are universal, right? But we also have to have length and volume. So we've talked about kilograms. That's going to be our unit of volume, is kilograms. And so, again, I want to make sure that throw in the caveat that the weight and volume don't necessarily mean the same thing. right? So kilogram is a kilogram. But weight is the effects of gravitational pull on that unit of volume. And so let's say we have two things that are exactly the same size. One's made out of aluminum, which has got a little bit of aluminum on it, I think so. It's also got a magnet in it. But one's made out of aluminum, one's made out of lead. Exactly the same volume, right? Because we've got the same stuff here. But does aluminum and lead weigh the same? The answer is no. Lead's very heavy as opposed to aluminum's relatively light in comparison. So we've got unit of volume being the kilogram. We've got length being the meter. We're American. We like feet, inches, yards, things like that. But the scientific standard is going to be meters and then seconds. So what you have then are you have to have a couple of different things in order to make a measurement. I like to use the example of driving to a town. So Jacksonville is just south of us. It's the next big town. You got to go through Flint and Gresham and Bullard. Eventually you get to Jacksonville. So if somebody asked me, if they weren't from around here, and somebody asked me, how far away is Jacksonville? I said about 30. Okay, 30 what? 30 what? Is it 30 minutes? Is it 30 kilometers? Is it 30 miles? What exactly is it? So we have to have a unit, and we also have to have a magnitude. So magnitude is how many of that unit you have. So if I said 30 miles, it makes more sense than saying 30, right? So we have to have two things in order to make a good explanation of what a unit is. We have to have magnitude, and we have to have that unit as well. So those are the units that we're going to use, and everything is going to have both a unit and a magnitude. All right, so then we start into mechanics. So mechanics, what we're going to talk about again, you don't have to work these, you just have to be able to describe the formula or answer a question that describes the formula, from just the words used. So velocity, we talked about velocity the other day. What is velocity? Yeah, speed. Velocity equals speed equals distance over time. Right? So it's a distance you travel over time. So if somebody were to say, how long would it take me to get to Jacksonville? How would I express that? Yeah, the distance is 30 miles, right? And if it takes you 30 minutes, it'll take about 30 minutes. How fast are you going? 60 miles an hour, a mile a minute, right? So that's your velocity is 60 miles an hour. So distance over time is velocity. So average velocity is just like finding the average of anything. How do you find the average of your test grade?
Add all of them up and divide by how many?
Yeah, so you add it all up and then you divide by the quantities that you have. So we'll have 6 to 7 tests in here, so you would add all those numbers up and then divide by how many tests we complete. So that's going to give you your test average. So average velocity is velocity that you finish with minus velocity original over the time it took you, over the number, in this case it would be over 2. Okay, so that's going to give you your average velocity. And so, anybody ever been to the drag races? Nobody?
Yes.
Okay. All right, so Bushong needs to update his book because the velocity of his dragster in this book is, I calculated it out one time, it's about, and he's got a rail dragster, which, top fuel dragster. I think if I remember right, it works out to be about 170 miles an hour. How fast a funny car is a top rail going now? Anybody know? Over 300, right? So really, really fast. His dragster is kind of lacking. So anyway, average velocity is your, let's subtract, it's add. We'll get to subtract here in a minute, in acceleration. So I always want to try to combine average velocity and acceleration and kind of create my own formula. So you got average velocity, add the two together, your ending, your original, divide by 2, and you have your average velocity. Then you've got acceleration. Okay, so what is acceleration? Well, we talked about that the other day. You're trying to pass somebody, that tractor that we'd mentioned. I'm really not as aggressive of a driver as what I let on. But it's the change in velocity. It's how much of a velocity pickup you get. You know, if you're starting at 0 and you end at 310 miles an hour for top fuel dragster, that's a lot of change, right? And the time that it takes to get there, in that example, you're looking at just over 3 seconds, just under 4 seconds, something like that. So it's really, really fast. The acceleration is really fast. And drag racing, you know, I really recommend, you know, if you got nothing else to do and you're in the South Dallas area, Ennis has, you know, they run the top fuel through Ennis, and it's worth going to at least one time. You have not seen, heard, or felt horsepower like you will in a dragster unless you go to the actual show. You can't sit down in the bleachers. You'll see whenever the car starts to take off, everybody stands up. That's because everything rumbles. You're looking at 2 different cars taking off at 15,000 horsepower, something like that. So the seat rumbles. You can't stand still, but you don't want to sit down because it rumbles the seat so bad, but it also rumbles the ground so hard that, you know, you're dancing, you're kind of picking up your feet. Real power, crazy power. The closest other thing that you might find is monster trucks. Anybody ever been to one of those? Yeah. So they're coming pretty close, but they're not staying on it quite so hard as what top fuel dragsters are. So acceleration, change in velocity. So now we've got, you know, kind of what I was going with before, and that is your ending velocity minus your original velocity over the time it took to get from one to the other. Okay, that's your acceleration, it's your change in velocity. So a couple of things. So on the test, you know, you've got to understand the formula itself. Okay, so what you'll hear us telling you is it's not just enough to memorize the thing. So I give you a question that says what all do you have to know about acceleration? Well, no, let's not even go with acceleration. Let's say average velocity, because acceleration is pretty obvious. So average velocity, what do you have to know? Yeah, you have to know the finishing velocity and beginning velocity, but what is velocity? Distance over time, right? So do you have to know a little something about time for average velocity? And the answer is yes. You have to, you know, again, you're not going to have to work it, but you're going to have to understand that time goes into that, time goes into that, time is, you know, defined in that one and this one. Okay, so acceleration. Now we got Newton's 3 laws, and you're familiar probably with at least 2 of these, if not all 3 of them. If you've taken any kind of physics class, you are. So force. Force equals mass times acceleration. All right? So force is equal to mass times acceleration. So again, what you need to know in order to work this out is the mass of the thing, how, you know, much of it is there, plus the acceleration, the change in velocity. How do you find change in velocity? You have to know the velocities, right? And in order to know the velocity, you have to know how far it goes over a period of time. So force. Also, what you'll find, described sometimes is that force, if you apply force to something, then that something is pushing against you as hard as you're pushing against it. Okay? And I think that bears a little bit of explanation. So, you know, if I push on this thing up here, this podium up here, or on this wall, who's doing all the work, the actual work? I am, right. But where is the force applied?
To the object.
To the object, but is the object moving? Not in the wall. In the podium it did move a little bit, but it's not moving. But where's the actual force realized? Right there. Why can't I move the wall?
Because it's attached to the building.
Because it's attached to the building, and it's got gravity pulling it down, right? So even if it was a freestanding wall, would I move it? It's not actively pushing against me, but is there a shared force there between my hand and the wall? And the answer is yes. So if you run into something saying something similar to, you know, if you push against something, it's pushing against you as hard as you're pushing against it. That's what it's referring to. That's not on the test, but you know, just in case you bump into that and you're going, no, I'm doing all the pushing. Well, not really. You got gravity, you got all kinds of stuff, forces that are causing you not to be able to push the object. So weight, we've already talked about weight. What is weight?
Force of gravity on a mass.
Gravity on a mass, right. Gravity on mass. So what the weight, you know, we have a tendency to look at light things and equate them to things that are light as well, right? So, you know, there's old saying, what weighs more, a ton of rocks or a ton of feathers?
They're both the same.
They're exactly the same, right? So practical application of this is that, you know, I had a patient one time, and actually this happened 2 or 3 years in a row, old farm boys, maybe not, probably not farm boys, probably people who were working with farm boys. So the big bales of hay, the big round bales of hay, 700 pounds easy, right? And so, you know, one's trying to roll off of a truck and somebody tries to stop it. But it's already, you know, the velocity has gotten too much for them to actually stop it. I've seen broken backs from people trying to stop these things. They roll off onto the person. Okay, now you've got the velocity where they could not stop it. You've got the acceleration of gravity and weight coming off the truck. It lands on you, something's going to give, right? But it's all grass. Yeah, but it's 700 pounds of grass, you know? Like I say, I've seen young men, suddenly their body is jerked into a 90-year-old man's body, paralyzed from the chest down, because they broke their back trying to catch grass that was going to the grass, right? So something big starts moving, it's got momentum, which is what we're going to talk about in a minute. Momentum, we've got velocity, we've got weight, gravitation, well in this case we've got gravitation, you know, in the form of weight. You got mass, just get out of the way, you know, if cars going too fast. Yeah, you've seen YouTube page videos where people try to get in front of a car, stop it from rolling. 3,500 pounds. You know, you're $160. You think you're gonna stop that car? Only if it's rolling really, really slow. All right, so anyway, which brings us to momentum. So momentum is mass and velocity. So we just kind of talked about that. You got mass traveling at a specific speed, momentum mass times velocity. It gets hard to write when it's down that low. So you increase either one of those things and your momentum increases, right? So you've got a 70-pound bale of hay. Is it hard to stop? It depends on how hard somebody throws it at you, you know? it'll still knock you down,
going
right? If it's
20
going
miles an
fast,
hour.
yeah, if it's going 20 miles an hour, it's gonna hurt bad, right? But if you've got that 700-pound roll of grass and it's only moving 5 miles an hour, you're still gonna get hurt, right? So momentum is mass times velocity. Work is force times distance. Force times distance. And then power. Power is work over force. So again, you've got to recalculate your, your force. You get your, it's the same thing as force times distance over time. So power, force times distance over time, right? So every one of these has some kind of time component. Once you get past velocity, in order to find any of this other stuff, eventually you're going to have to bring it all the way back to velocity, or at least incorporate some sort of time in there. So where do we use all this and why does it matter? Be what you're asking yourself. Well, let me show you some stuff. I got a couple of different things up here, or back here. 3 things. One is a complete X-ray tube, and the other are the main components inside the X-ray tube. Okay. So a couple of things about this. This tube, I think, already has a crack in it, so it's kind of fragile. If it has, and it's a vacuum tube, just like it's basically a big, expensive light bulb. So you drop an incandescent light bulb, vacuum tube, and what happens? It shatters and it goes kaboom. Okay, so this is thick glass in a vacuum, providing the vacuum is still, in the tube. So if it hits the ground, it's thicker glass and a bigger vacuum, it's going to sound like a bomb went off down here and they're going to evacuate the building. Okay, don't drop this because it's going to make a lot of noise. It's going to scare a lot of people. That's number one. And number two, I can't replace this. Okay, the only way I get X-ray tubes is if they take apart a machine and give me the X-ray tube. So these X-ray tubes that I've got, and we've got some more up in 215, they're tubes that don't work anymore. Okay, so what I want you to pay attention to in this is a number of different things. Inside of this X-ray tube, don't roll, are these two components. Okay, we've talked about these two components quite a bit. So, and you can, take a look at these and then you can look inside of the X-ray tube and see them. They're not very far apart. They're only about that far apart inside the X-ray tube. This has 2 filaments in it. What do you think this is responsible for? 2 filaments. Thermionic emissions, very good. This is where the electrons come from. Okay, so we run a current through this and we get, that heats up just like a toaster. It's no different fundamentally than a toaster. A heating element in a oven, it's the same thing. Okay, so it's got 2 different filaments. You don't use both of them at the same time. You use only one of 2. If you saw the control panel video I did, the small one is whenever you push the button for small focal spot, that's the one you're using. If you push the button for large focal spot, you're using the big one. Okay, that's what you're looking at here. And this is the anode. So the anode is kind of heavy, so be careful with it too. Don't drop it on your foot or anything. But it's tungsten for reasons, mainly tungsten, for reasons we'll talk about later in the semester. Okay, so when we make X-rays, we create a space charge, thermionic emissions, off of one of these, whichever one it is that we select, and we send them across the tube really, really fast. Velocity, bingo. Also though, they go from nothing to maybe a third the speed of light going across the tube. What does this sound like? Acceleration. Right, so you push the rotor button And what happens is you also, if you'll take the x-ray tube once you see it, and you kind of turn it, this is not the best x-ray tube. I think that the bearings on it are a little bit spent. They're not completely terrible, but if you turn the x-ray tube, then you can see that the anode, yeah, it's cracked. So you can see that the anode turns. All right, so I'm turning it real quick and the anode stays still. Okay, so when you push your rotor button, what happens is this thing right here is an electromagnet. All right, this is the motor that turns the anode. When you push the prep button, what you do is when you see this, what you'll see is that wires go into individual places inside of this thing. So what happens is that we push the rotor button, you get that collection of electrons on the anode, or on the cathode, really, rather. And at the same time, you get alternating current that's going through this coil of wire. So that alternating current is going through each one of these individually in a specific sequence, so that what it's like is you're taking a magnetic field and you're running it around and around this way. Okay? So that's what you're hearing, is a spinning of the anode whenever you rotor up. You rotor up, and because this is going around and around like that, it's spinning that anode. And we'll get deeper into that later in the semester. But it's spinning the anode, okay? So it goes from 0 miles an hour to, well, it's really RPMs, revolutions per minute, to about, with the acceleration, it goes from 0 RPMs to about 3,000 RPMs in 1 second. Really quick. So it's spinning really quick. Okay? So when we make our exposure, then, what we're going to do is we're going to take the electrons that are gathered here and we're going to accelerate them across the tube at really high rates of speed so that they smack into the anode. All right, so what's the anode made up of? Tungsten, which is a element which is made of atoms, which are made of protons, neutrons, and electrons, right? So those atoms are going to be held into place with a specific binding energy, okay? Or the electrons will be held into place with a specific binding energy. So in order to dislodge those electrons, what we have to have is enough momentum to knock them out of place, okay? So if we have enough momentum to knock them out of place, we make x-rays in 2 different ways. One is just because it slows down, and the other is because we knock those electrons out of place. Remember what we call those two different ways? Brims and characteristic, right? So the characteristic, we have to have enough momentum caused by the acceleration to apply a force that will knock those electrons out of place so that we create x-rays. What do we create mainly? Well, yeah, in the x-rays, brims, heat. And we're going to deal with that here in a second. Heat is what we mainly make, a little bit of light, and just a few x-rays. The 2 x-ray types that we make, 85% are going to be brims, and the rest are going to be characteristic. The brims happens because of loss of energy. The characteristic happens because we knock the electrons out of place using all of this stuff, right? So velocity. We see that in the acceleration of the electrons across the tube. The faster they go, well, the higher the kVp we apply, the faster they go across the tube, and the more likely we are to be able to do the work that we want to do, and that's create x-rays, okay? So average velocity, you know, I don't know. I don't know what the average velocity is. It's, you know, the difference between however fast we can get them up to versus when they weren't moving, you know, divided by the 2. So if it's third of speed of light, then it goes from, you know, 0 to a third of the speed of light. That'd be a sixth of the speed of light. I don't know. I'm just spitballing numbers here. I have no idea. So acceleration is what occurs whenever we push our exposure button. All of that other stuff just occurred whenever we were rotoring. right? So we actually get velocity in the speed of the electrons, but we also get the velocity in the speed of the rotor, right? That's a different type of force. Force applied in a circular motion, you know what that's called? Somebody knows. What's that? It's rotation. There's torque,
Oh,
right? So the torque on, you know, X-ray tube, you could reach up and grab it and stop it with your fingers. Yeah, it's not high torque, but it is torque. All right. So what did I miss? Gravitational pull, weight. It's kind of heavy. Really doesn't have a whole lot of application here. But power. How do we express electric power? Volt is, yeah. I don't want to say no, because yeah, that's what we call the strength of our X-ray beam.
Per second.
You see it on a light bulb, huh? Hmm?
watt.
That's a bad dad joke. Yes, wattage. It's wattage. So power is electric power is measured in wattage. Okay. So I'm gonna pass these around. I'm gonna pass the tube around first. Yeah, I'll pass the tube around first. I'll pass the other components from the other side. I'm not gonna pass this around. It's, you know, it is. Copper. Okay, so y'all good with all that?
Yeah.
As good as we can.
Good as you can be. Again, it's been, you know, if you've got the Bushong workbook, he probably has things in there, you know, math problems you can work out for all of that. I'm not gonna make you work any of those out.
Where does the power apply, like in the tube, or?
Oh, good question, good question. In the X-ray tube itself, it doesn't, but our machines are gonna have a power rating. Like our machine upstairs may be a 25 kilowatt X-ray machine, okay? So in the tube though, you know, we just break down to kVp and mass. Okay. Yeah. Oh, I didn't finish up Newton's 3 laws. I'm sorry. So, yeah, before Newton, he got cracked in the head by an apple, and then I totally ignored 2 of his laws. So we got force. You're familiar with that. I skipped over his first law, which is inertia. What is inertia?
Oh, something at risk is
What's that?
Body at rest stays at
Body at
rest.
risk stays at
There you go. It's the definition of and that's how we usually think of it, as body at rest, body in motion. It's resistance to change, right? You got to understand some of this stuff doesn't really apply within the Earth's atmosphere, you know. You know, if I were to toss the pen across the room, I'm going to use one of their ratty pens, markers. That is theirs, right? Yeah. If I throw it across the room, what's going to happen? It's going to hit the ground. It's going to stop, right? But it was moving, according to Newton. Shouldn't it just go on forever?
Gravity.
Gravity, exactly. We got weight, gravitational pull on the pen. It's going to hit the ground, and we've got friction. Even if it, thank you. Even if we didn't have the ground for it to hit, if this was a gas planet, it would still stop. Why? Force of friction, exactly. So eventually the molecules would slow it down and it would come to a stop. Right, it would eventually come to a stop anyway. So that applies, and Newton was a genius, you know, he came up with this, just observing the stars. I mean, this is 1600s. But he hypothesized that if we were to put maybe a cannon on a high enough, you know, the highest mountain, and we were to shoot it, then the cannonball is eventually going to hit the Earth, right? But if we could shoot it hard enough, to get outside of the direct gravitational pull, it would orbit the planet forever like a satellite. So, I mean, I wouldn't have come up with that, right? So that's inertia. Body at rest stays at rest. Body in motion stays in motion unless it's acted on by external force. So the reason the pen would have stopped is because it was being acted on, by the force of gravity, plus the ground, plus the atmosphere. So I think I might have loaded this video into Canvas last year, and if it's not, I'll try to find it. But there was a guy that I don't know, it was probably 15 years ago or so. He wanted to break the altitude skydiving record. So he couldn't fly in an airplane to get up to this height. The SR-71 or U-2 might be the only things that would get that high. You could see the curvature of the Earth, how high he wanted to go. It's like 115,000 feet. Had to wear a spacesuit essentially. And so he got a helium balloon with a capsule in it to keep him warm, and he goes up to the edge of space and he opens the door and he steps out. So I dropped this. How long does it take to get to the ground? Yeah. So acceleration of gravity is 9.8 meters per second squared. This guy fell for 5 minutes. That's just insane. I've never been skydiving. My son has. He said you get out of the airplane, you got like 10 seconds, you got to pull the ripcord. 5 minutes this guy fell. He broke the sound barrier in his fall. Okay, so what is the reason I bring that up is, what is terminal velocity? What's the fastest animal on the planet? I'm not talking about a land animal. Peregrine falcon. How fast can it dive? Yeah, like 200 miles an hour. That's terminal velocity. If you were to drop a ball off of a high building, it would get to terminal velocity. Excuse me. And that terminal velocity would only be about 200 miles an hour. So how fast does sound go? 700. Yeah, it's like 750 miles an hour-ish. 750 miles an hour. So how did he break the sound barrier?
He was outside of it.
What's that?
He was outside of the atmosphere.
Yeah. You ever been to Colorado? We're flatlanders down here.
Yeah.
What is it like the first day you get to Colorado and you walk upstairs?
Can't breathe.
You can't breathe. Right.
Different.
You can't breathe. It's the atmosphere. The atmosphere. So the atmosphere at 115,000 feet, how thin do you think it is? It's really thin. So you got two things going on there. One is you don't have the atmosphere that we've got down here. That's number one. Number two is that the speed of sound, kind of like speed of light, we're going to talk about that later, if it enters specific medium, it will distort, it'll change, right? So underwater, sound travels faster than what it does here, which travels faster than what it does at 115,000 feet, okay? So speed of sound at 115,000 feet may be, I'm again spitballing 500 miles an hour. And again, there are not as many molecules to slow him down. So you may be thinking, okay, he's falling at 600 miles an hour. How does he stop? Pull a ripcord at 600 miles an hour, what's going to happen to you? You're going to know rip, because it's going to tear you in half. So how did he survive that? The guy's, as far as I know, he's still alive today. What did he enter? The atmosphere, right. So what's the atmosphere full of? Molecules, right? So he fell through Colorado and he fell through New Mexico and he wound up, in a thicker atmosphere, and each one of those atmospheres he came through, he slowed down to terminal velocity. If he was just standing, if he was kind of pencil diving, he'd go 200 miles an hour. If he flattened out, about 120, pull a ripcord, float safely to Earth. He passed out during that dive. He lost consciousness. He went in a flat spin.
No.
and he passed out, and fortunately he woke back up, you know. But anyway, if it's not in canvas, I'll put it in canvas.
He went in a helium balloon?
He went in a helium balloon all the way up to the edge of space. Yeah. It's one of those weird looking helium balloons that are real tall. So,
How did it not like lose air in that, like when he went outside of the atmosphere?
yeah. I don't know all the specifics behind it. Maybe helium doesn't contract as much, or maybe he had helium containers to continually inflate it. Yeah, yeah. So I was more impressed with. I wouldn't go up to 115,000 feet and jump out of a balloon.
Absolutely.
You know, I mean, I've
Especially
done
if
some
you're seeing
stupid things in my life, but no, I'm not doing that. So, so anyway, that's inertia. We talked about force, and the other one is action reaction. That's kind of what we were talking about in force before. With every action, there's an equal and opposite reaction. I'm pushing on the board as hard as, you know, the board's pushing against me. And you can see that in other places as well. In movies, it is so greatly over exaggerated. You see somebody get shot and they fly through the air 50 feet. It just doesn't happen, y'all. You know, it's theatrics. If you've ever shot a gun, though, you feel it. You know, a rifle, it it kind of kicks your shoulder a little bit, right? Slugs, yeah. It'll, if you're shooting a shotgun with slugs, it's gonna kick. So that's action reaction.
Yeah, you get a purple shoulder.
Yeah, exactly. The load's going one direction, the gun's going the opposite direction, but the gun's got weight, so it, it doesn't blow your shoulder off or anything like that. But anyway, those are Newton's 3 laws. I don't think I missed anything else until we get to energy, right? So energy we kind of talked about, so we're going to not spend just a whole lot of time on it. Energy is the ability to do work. Potential energy is stored energy, and that's what we call KVP. And there's a certain amount of anxiety that comes with KVP, and whether it's potential before the electrons start to move or after the electrons start to move, and you'll just need to flush all that, essentially. Just think of KVP as your potential, okay? So we're not going to get so specific as to say exactly when the potential is applied. The potential is applied whenever you mash the button and electrons jump across the tube. So we adjust the KVP at the auto transformer, we create the KVP at the high voltage transformer. We don't apply it until we make our exposure. We're not creating X-rays until the electrons jump across the tube. It's like a snake over there, isn't it? I don't want to touch it. I don't want to keep it. So the anxiety is, I think that, we say KVP affects it is potential, but we don't have X-rays until you apply the KVP. So, it's kind of a circular thing, and that's why I say just flush all that and just think of KVP as your potential. That's your tube potential. That's what creates, our penetration, our beam quality, all those things that we'll talk about later in the semester. But we're not going to get real specific into where and why KVP is applied. Okay, so don't stress over that. All right, so potential energy, kinetic energy is movement of electrons. I've also had students get a little bit stuck on the movement of electrons through the filament. Okay, when we're talking about potential energy, we're talking about tube current. So we don't have tube current until we mash the exposure button and they jump across the tube. But we got kinetic energy going through the filament. Yeah, you do. In the form of amperage, it's going through the filament. But in as much as having tube current, you don't have that until you make your exposure. Okay, so that's what we're referring to in potential as it applies to the electrons sitting on the filament. But the main thing that we create, we've done this, we create heat. So we've got to deal with the heat. The main thing that will destroy your X-ray tube is heat. Overwhelmingly, what's gonna happen that causes X-ray tube failure is heat in some way or another. Okay, we're gonna go through all the different ways that it could happen. What's the time?
We have 30 minutes.
You got, oh, good. Okay, so there's a lot of different ways that we can get to tube failure, and all of them, with the exception of rough handling, have to do with heat. So we got our X-ray tube, and the anode has to spin on something. So it's very well balanced. This one's not as well balanced as one you'll see later. I'll bring the other one down at some point. It's in better shape. It looks like it's brand new, never used. I don't know how we got it, to be honest with you. But we'll take a look at it, and you'll see how well balanced it is. You can't turn it without the anode doing something. Okay, so it's very, very well balanced on bearings it has to spin on. So what we've got is X-ray tube, and we've got, in our X-ray tube, we've got anode, and then we've got the cathode. So we create thermionic emissions here, right? So we'll also refer to that as a space charge, electron cloud. So we'll use all of those, okay? All those mean, for our purposes, the same thing. They're all the same thing. But, you know, this is what I want to focus on: thermionic emissions, hot ions. We're going to create hot ions. So if you have something that you run a current through and it gets hot, glowing red hot, eventually it's going to burn out. Okay, we'll make it out of tungsten, and for reasons we'll talk about later in the semester, that's tungsten, that's tungsten. It's a different alloy in each one. We'll talk about that as well. But it's tungsten, which has a very high melting point. But if you've ever dealt with incandescent lights, eventually they burn out. Okay, so when they burn out and you unscrew them, and they're becoming more and more rare. But if you unscrew a burnout incandescent light bulb has a filament in it. What do you see? It's what you call open filament. So eventually that can happen. You can burn it out, and that's what we refer to as an open filament. Why did that happen? Burn it up, right? But what else do you see on that light bulb? Usually around the base of the bulb. Black, yeah, it turns black. So what you're seeing there, some of that dark area right around the base, is a part of the filament that vaporized before it burned out. Okay, so if you have an old light bulb that hasn't burned out and it's incandescent light, you can unscrew it a little bit and you can look at it, and chances are you've got some of that going on. So that filament will get so hot that eventually it melts and it vaporizes and it coats the inside of the X-ray tube. Should have used a different color. Okay. For whatever reason, our filament vaporizes and it turns orange instead of black. So to coat the inside of the X-ray tube, that's what we refer to as tanning. Tanning of the X-ray tube is caused by the vaporization of the filament. You may get a little bit off the anode tube, but it's primarily vaporization of the filament. Okay, so you've got a very thin layer of tungsten now on your X-ray tube, on the inside of the X-ray tube. Okay, I'll get there in a minute. So we've got two different things going on. One is eventually we're going to burn it out, and two is that we're going to tan the tube. Okay, so how do we make X-rays more safe? Okay, and this is, okay, I want you to know this, but this is not really for this test. This is explanation of why we do the things that we do to try to keep the tube cool. We fail, but we try. Okay. How do we make X-rays safer for the patient?
Filtration.
Filtration. So what do you suppose we used for filtration?
Aluminum.
Aluminum, right? So if aluminum absorbs a little bit of X-rays, what do you think tungsten will do? absorb more, right? So with tanning of the x-ray tube, what we get is an increase in filtration. So we remove more x-ray photons from the beam. So what are we gonna have to do? Turn it up a little bit, which is going to make that even hotter.
It's gonna make more.
It's gonna make more of that. We're gonna have a negative feedback system that eventually
Burns it out.
burns the x-ray tube up. Right, so this has to spin on something. So we've got these little ball bearings in here. So we've got, or some sort of bearings in here. If your bearings get too hot and they're greased, you can't get back in there and add grease to them. They're greased, and that's all the grease they're ever gonna have, and those can wear out. They can wear out because we've got rotation on them. Rotation causes friction, right? Do you think that all the heat's gonna stay right here? No, it's gonna go all over the place, all right? So the heat is going to conduct throughout the x-ray tube. Conduct. That's barely legible, but you get the point. It's conduction. It conducts all through the x-ray tube, so it spreads out, okay? All right, so we got tanning. We'll deal with that here in a minute. These can eventually wear out. If they wear out, eventually it could cause the anode to stop spinning. The purpose for the spin is to, again, conduct the heat across the entire face of the anode. Okay, so now let's talk cast iron skillets. Okay, anybody done any camping or cook with cast iron on stovetop? Okay. So if you're cooking with cast iron, I got a skillet that's like this big, right? So do I put that on the smallest burner I've got? You put it on the biggest one that's as big as the skillet. Why? Well, because if I'm cooking off that little bitty one, it's got to conduct, it's going to get real hot right there in the middle, but it's going to have to conduct, to a greater area, right? So if we apply, let's say this is stationary, this anode doesn't spin, and I apply all that heat to just one area, what's going to happen to that one area? It's going to melt too. So if I spin it, instead of the heat being stuck in just one spot, what's going to happen?
Disperse it.
It's going to disperse it, right? So is it just going to stay on this area right here? So if I use that big cast iron skillet on a small, a small burner, will I eventually be able to cook out on the periphery?
Yeah.
Is it going to? Yeah. Why?
Conduction.
It's going to conduct, right? So the conduction is going to go all over the face of this thing, okay? Did you notice the size difference between this anode and the one in the x-ray tube? This one's a lot bigger, right? So which one do you think can hold more heat?
The bigger one.
The bigger one, right? Okay. So more on all that here in a bit. I think it's ever more going to have arrows on it. All right, so we rotate the anode in order to spread all that stuff out. Reduces the heat. So we've got tanning. Again, this is not for this test, but glass is a poor conductor of electricity, okay? So it's a pretty good insulator. You have conductors that allow electrons to flow. You've got insulators that stop electron flow. It's really a pretty good insulator. But what if I put a layer of metal down? What are wires made out of? Metal, copper, some sort of metal, right? So I've got a layer of metal on the inside of this thing now. Is that bad news? Well, potentially, because I want electrons to travel from here to there, but electrons, the flow of electricity is much like water. We know about rivers.
They go.
They meander.
Yeah.
Why?
They find the quickest
Path of least resistance, right? So what if the path of least resistance now is not from here to there, but rather from here to there?
Then you're burning up those wires.
You're going to blow your tube. That's what we call arcing. Okay? So all of these things go into, and there's other things as well we'll talk about later in the semester, but all of these things have one thing in common. Bearings wear out, because of heat, friction plus conduction. Tanning occurs because of heat. Arcing occurs because of tanning, which occurs because of heat, right? So it's all about heat, and we got to deal with heat. So we have three different ways to deal with the heat. We've got conduction, we've got thermal radiation. Okay, just the words, what does that mean? What is radiation? Transfer of now energy in the form of heat, right? And the other is convection. Okay, what is convection? Anybody got a convection oven? Bingo, bingo, circulation. So you turn on your convection oven, no idea how to use them. What happens? It circulates the air inside. So inside of your oven, you're gonna have hot spots. If you ever do any grilling, you know eventually your grill's gonna have hotter areas, you know, where you can cook faster and cooler areas, regardless of what the setting, you know, that you got with gas or whatever. So if you blow that air around, it evens that out, right? That's convection. So how do we use those? Well, we kind of dealt with conduction to a degree. We're gonna get rid of all this and just remember tube failures because of heat. You don't see the X-ray tube because it's in what we refer to as a protective housing. That protective housing is full of oil. And I pronounce it that way specifically because, you know, I've got listeners in other countries that don't know what oil is. Oil is full of oil. All right, so we've got creation of heat, we deposit the heat conducts all the way around this, but we've got a space in between the X-ray tube and the protective housing. So what we've got then is that we've got thermal radiation, and well, no, I'm sorry. We've got thermal radiation from the anode to the glass. Okay, it just radiates out to the glass. It's not going to stay right here. It's going to radiate out to the glass. The glass is touching the oil. Right. So conduction is the spread of heat by touching. Okay, so we got conduction here. We got thermal radiation. The heat's going to go down there, and then it's going to conduct again into the oil. Okay, so we've dealt with two of those. Your tube design is also going to have some sort of fan in it. And a fan, it might be a motorized fan, or it may be what they refer to as a bellows type fan. So what do you know about a bellows? It's those things that you see like in movies where the blacksmith is pumping this thing and you see it kind of collapse and the fire stokes up and, you know, it gets off of it, and yeah, it's a bellows. So in the X-ray tube, what it is it may be kind of like a single shot fan. Okay, so we've got this bellows thing up here that, let's say, its natural state is for it to be inflated. We get all this heat, and heat does what to air?
Rises.
You know, it rises, yeah. Anything else? Makes everything expand, right? You can see this, you know, if you go home, if you happen to have a balloon at the house, blow up the balloon, tie it off, stick it in the refrigerator. What's going to happen to it?
It's going to compress.
It's going to compress. You take it out of the refrigerator, you let it heat up, and what's going to happen to it? Yeah, so anybody ever been to the Great Balloon Race over in Kilgore? They take the balloons out of the truck and they lay them down and they hold them up and they light the burner. It's really worth seeing once. And they light the burner, and what do you suppose happens to the air when they light the burner? It heats up, and what happens to the balloon that's right now laying on the ground? Yeah, it rises. It expands and it rises. Okay? So what happens with the bellows thing is, in its natural state, it's expanded, but as it heats up, it squishes all this and it blows the hot air out into the room. Okay, so with it blowing the air out into the room, what do you suppose it's doing? is taking some of that heat with it. As it cools down, it reinflates, sucks more air back into it, and further cools it down. Okay? So we cool the tube down 3 different ways. We spread out the heat, and that's with conduction, right? We thermally radiate from the anode to the glass, and then and the best we can, we convect it out of the room. Again, that might be an active fan, or it may be a more of a bellows type fan. Usually, you don't hear that fan. If it's an active fan, you don't hear it. It's inside the protective housing. There's just too much stuff to actually hear it. If you're working on a machine and you actually hear a fan kick on, that's usually to cool down the light bulb that you're using collimate. That's usually what that is. It's the incandescent light bulb inside, and it's just getting too hot, so the fan kicks on to cool it down. But there's some sort of fan inside of there to cool the X-ray tube down. Okay? So what do you need to know about all that stuff? The arcing and that's later in the semester. I was just trying to explain how the tube is gonna get destroyed. And it's all, with the exception of possibly rough handling, you banging a tube around, it's going to be from one thing primarily, and it's gonna be heat, right. The main thing kills the tube. Ways that we get rid of the heat will be on the test, but the specifics of the tanning and, failure of the bearings and all that. Any questions? I'll leave it to you to work through the, if you want to do some calculations on Fahrenheit to Celsius, Celsius to Fahrenheit. I already gave you the answer to the test if you were listening. So, yeah.
So I'm wondering if we're gonna do any math, is it gonna be like trying to?
That would, if you're OCD and you feel like you have to work out the question on Celsius to Fahrenheit, Fahrenheit to Celsius, that's on you.
Okay.
All right.